So welcome to your 7th class in data analytics, where we explore interactive visualization, probabilistic modeling, and machine learning with Mathematica. As you will recall, we spent the first lecture talking about the concept of data analytics, right? And then we spent the next the next 2 lectures on the foundation of Wolfram Mathematica, both as computational, scientific computational platform, and also software ecosystem, and also the nitty-gritty of primitives of programming, right? And then we spent the next 2 weeks on interactive visualization. And I underline again the message of visualization as being very powerful tools in in some of the data analytics application. If you can visualize the right schema, you get the insight that's actionable right away. Sometimes the visualization help guide your model building effort. So you need to get to know your data, and that's where the visualization comes in. And then after you've done your analytics, you build your predictive model, let's say, you still need to communicate the result to the user, and that's where visualization comes at the end as well, right? And interactive visualization just means that you can, the user can adjust the perspective and basically view data from different angles, view result from different dimensions, and so forth. And you can also display how various parameters affect the system. In terms of education, interactive visualization is very good. I might give you an example that when I was an undergraduate learning about economics, like macroeconomics, we have like an ISLM curve, which depends on certain parameter and coefficient. And so we have to imagine or use, pen and paper to draw out the relationship so I can figure out what this coefficient does to the model. But if you had an interactive visualization, then you can adjust the parameter in real time and see what that result in the model is, okay? Right. So last week we started on interactive visualization. We start on probabilistic modeling, all right? And again, this is, you can think of this as the very first form of data analytics, okay? In fact, in a way, you could even say that it predates visualization, because if you can visualize the data with a histogram, that's already like a plotting tools, right? Even before that, you have a table of numbers. So what can you do? You can summarize what your data look like by applying basic summarization statistics, right? So where's the average and so forth. So last week I apologize that I think I had to enter the software key and I didn't have it with me, so we couldn't do it systematically. So let's do this lecture in a more systematic way. I'm just going to proceed according to the textbook, which is I designed to be very methodical. Right. Now, as with tradition, I will have 3 modules when it comes to probabilistic modeling. So the first one is descriptive statistics. Second one is probability model. And the third one is when you actually do inferential statistics, right? So let me squeeze everything down and show you the highlight. Oops. should have done this. Okay, right. So descriptive statistics, again, is about creating a numerical summary of your data. Okay, and I gave you an analogy that you go to a new place and you measure, say, the height or the weight or the width of the population, and you want to get an idea of the distribution of the size so that you can send the size distribution to your factory back home that can then make t-shirt or something like that. Okay, and you didn't have a way of communicating. You didn't have a way of sending the whole table of height and weight measurement. So you have to summarize it, right? So you send it, so summarize it with the mean and so forth, right? So let's let me just quickly. I just want to show you that. Oops. Oh, that's okay. Right. So let's proceed sort of like step by step. Okay. So first thing is moment and central moment. And again, this is what's the moment? Moment is basically an average of power of the numbers, right? So the first moment is the average of x to the power 1. So just average of the thing itself. So that's the mean, right? So I gave an example. Okay, so this is my example data set. Oops, sorry, I haven't generated that. Okay. Now, you'll see that so this is fallen from the book. I created some demo data. Okay, the first one is just some number. It's called the first 8 Fibonacci. Well, that's what it is. It's a table of 8 Fibonacci number. The second one is 2000 normal. So these are all example. Okay, so this would be like first example data set, second example data set, and so forth. Now, so the central moment, okay, the first moment is basically an average of individual data point raised to power 1. Okay, so that's basically an average, right? So if I have a Fibonacci, the Fibonacci number, so the first number is 1, 1, 2, 3, 5, 8, right? You take an average of the first 8, you get to 27 divided by 4. Now, all this are kind of the first number you report. Like I said, you have a bunch of numbers. You cannot send the whole number. You didn't have a fax machine. You didn't have an email. All you have is just a telegram, okay? So what you do is you take the measurement of all the heights of the potential market, right? And you take an average and you report that number, okay? And what's the second moment? Second moment is you take the average of all the numbers square. Third is average of all the number to the power 3, and fourth moment is to the power 4. Now, these mean nothing in itself, except maybe the first one. The first moment makes sense. It's a sense of average, right? Now, central moment, just say, instead of taking the sum of number square, you take the number, subtract the mean from it, right? And raise to power 1, raise to power 2, raise to power 3, raise to power 4. So that will be the central moment, okay? And this is where you start to get this thing called second moment, which makes sense, which is to say that you take the measurement, you subtract the mean, right? And then you square it. So this would correspond to the concept of standard deviation. So this would be kind of like, roughly speaking, how far apart are the population from the mean, okay? So this is a difference between going to a population where everybody's 1.7 meters tall versus go to a population where on average, everybody's 1.7 meters tall, but some people are 1.6, some are 1.8 and so forth, right? Okay. And then without showing you in detail, the third moment is about how skew rightward. Well, all this would make sense when we look at a probability distribution in detail. And fourth moment is sort of like how wide apart. So for example, you can have a population that's on average 1.7 meter tall, but nobody is 1.7 meter tall. Half of them is 1.6, the other half is 1.8, for example, right? So even though you have the same mean, you definitely have different spread out, the degree of spread. So go back to the first thing is, well, instead of taking arithmetic mean, which is to take everybody, every value, add them up, divide by n, okay? You can do geometric means, okay? So this is example, okay? So I use a color just to make a schematic, right? So arithmetic mean, just simple add them up and divide by the number, right? So a plus b plus c plus d plus e divided by 5, okay? Now, geometric mean is different. Geometric mean is when you take the multiplication and you take, let's say you have 5a times b times c times d and take the fifth root. And then you have this thing called harmonic mean, which is 1 over sum of 1 over, right? So this is very confusing. Why would you have this? Well, harmonic means is probably relevant to something like with electronic circuit. I'm not going to talk about it now. But do you know where you see geometric means? Anybody? Anybody? Well, if you have if you buy something, okay, you buy something, let's say stock, and it has, okay, let me go this one. Okay, you have stock price, stock S1, okay, is equal to 1 plus, let's say you have some rate of return, S2, S0, okay? Right? Does this make sense? Okay. So you buy stock today, right? And at the end of the period, you get 1 plus R. So let's say this is 5%. Okay. So it's 1.05. So let's say you start with 100 and you add 0.05. Okay. What do you get? Get this, right? Okay. Now, what about S2? S2 is equal to 1 plus 0.06 times S1. Okay, now you get this, right? So what's S3? What's S3? S3 is, let's say, 1 plus 0.04 S2. Okay, does that make sense? Okay. So let me ask you a question. Okay. So this is S0, S1, S1 become S2, S2 become S3. My question is, what's the let's say this is 1 month, 1 month, 1 month. So what's the average rate of return? Well, there are two ways of answering it. Okay. One way is arithmetic mean. So 0.5 plus 0.6 plus 0.4, right? Divide by 3. Who would say that that's the answer? That's the answer, right? Okay. If that were the answer, okay, let's say R on average, okay? R average is equal to 0.05, right? Okay. Right? If that were the average, then shouldn't S3 be equal to 1 plus R average times 1 plus R average? Should it? Should it? The answer is false. right? The answer is false because the average in this sense is arithmetic average. Okay, so I can do this. So this is R1, R2, R3, right? What is the right average to use here? It is geometric mean of, say, 0.05, 0.06, 0.04. Okay. Okay. Actually, if you did this, our geometric means, okay, and you did this, then it's correct. Oops. It should be close to correct. Oh. I made a little, it's actually a little bit more complicated than that because it's geometric mean of this thing. Let me do it again. Sorry. Let's say our geometric mean is 1. Okay, sorry. Okay, there. And then okay, that's true. Okay, right. In other words, you can take an average by adding and divide, or by multiplying by take the roots. Okay, so that's geometric. This is more relevant for statistics when you take a sampling. This is more relevant for financial analysis. Okay, does that make sense? Okay. So you see the difference between this and this, right? In a way, they both give you a sense of where the middle is. Okay, but this one is the middle by adding, and divide. Whereas this one is multiplying, and they take the root. Okay, this one is more applicable to finance because what happened in one period and the next period is related by multiplication, not addition. Okay, in finance, that's how return is calculated. So calculated is a multiplicative term. So that's why if you want to find an average like this, like historical return. Now, why do people in finance do this? When you look at finance, they do this. It's because they're looking at it from a sampling point of view. In other words, they take a sample of this period return, that period return, that period return, and they assume it's normal. And so they use arithmetic mean. Okay, I'll come back to this. Okay. Anyway, the point is that even the word mean, which is some kind of averaging, there are actually 3 definitions. Okay, there are 3 definitions, and they give different value, by the way. They give different values. Okay, you take the same 8 number, one is here, one is here, one is there. So it's different number. Okay. Now, what about median? Median, I told you, right? Let's be lazy. Let's be lazy. Let's say I want to know what the average is, but instead of taking the average of everybody, I'll just take an average of the guy who is in the middle. Okay. And if there are odd number, you line them up. The one in the middle, there's just one guy, right? If it's even number, there are 2 guys in the middle. Just take an average of those 2. Basically, that's the median. So it's giving you a sense of central. Where would the word median make more sense than median? Sorry, where would median make more sense than mean? Anybody? Usually when population is very skewed. For example, if you have a population that has a lot of poor people, okay, and one rich guy, okay, one rich guy. So one rich guy makes $1 million, and then there's 999,000, okay? So basically everybody else makes zero. If you take an average, right, that average is still gonna look pretty good. However, if you're talking about real population, like where the other half live, you know, the line separating by the richer half from the bottom half, well, that number can be very low. So if you have something that is very skewed, definitely like income distribution, mean doesn't mean anything, because when you have 1 billionaire in the population, that throws everything, everybody looks rich. Okay, makes everybody looks rich. But in fact, if you want to see how, you know, half of the people live, at what income level, the best thing is to line up from the richest to the poorest and go to ask the guy in the middle and say, how much money you make? Okay, that's the guy who stands right in the middle of the poorer half and richer half. So that would be the median. Okay, so median and mean are not the same. Now, it would be exactly the same for cases where it's symmetric. I'll show you later. So anyway, so mode, this is kind of so all this is kind of like a measure of, so let's do this. And the variance, okay, so variance is the second moment, right? Now, second moment, the measure of dispersion, the one that you used to is standard deviation. What standard deviation is the square root of the variance, okay? What else? Standard deviation is square root, right? Mean absolute deviation, that also works, right? The reason it's not, it hasn't been used in statistics because to calculate mean absolute deviation, you need this function called absolute value. This function is not mathematically very friendly. You can't take derivative. So nobody uses that. So that's why mean absolute deviation kind of makes sense semantically, but nobody uses it. Range, this is also good, right? Range is also like, well, how wide apart are the population? Well, you take the tallest minus the shortest. That's the range. But that range, again, can be thrown off by some guy who's very tall and somebody who's very short. So instead of taking the range as the distance between the tallest from the shortest, you do similar trick as you did with median. Except instead of taking the guy in the middle, you take the guy that's like 1/4 of a way to the tallest and 1/4 of a way to the shortest. And you ask how tall, how the difference in height between the 25th percentile and 75th percentile. So that's called interquartile range. And that's more useful. So anyway, all this definition is kind of almost trivial. You can do none of this. You need any kind of mathematics to do. You can use Excel. Okay. Now, measure of asymmetry. This is where, you know, the skewness we're talking about. So again, I can draw a quick picture. Oops. Can I draw a picture? Well, I'll draw a picture later. Okay, and this is called heavy tail nest. So let's go do that. Let's go to a little screen. Okay. Let's pretend I have data set. Let's pretend I have the data set. And the histogram kind of looks like this. Okay. histogram looks like this. Now, first of all, again, think of this as series of number. I happen to stack in the histogram because I can do visualization. Go back before visualization, summarize this with number. Where is the middle? Okay, so if I talk about average or X bar, okay, the middle, you can think of it as putting a little seesaw here and it balances, okay? Because you sum the distance from here and it's kind of like half to the right, half to the left in terms of weight, right? So if you add all the values here, whatever it is, this could be 107 and this could be 275, doesn't matter, okay? The middle is gonna be there. So think of it as a seesaw, as simple as that. That's called the mean, okay? Now, I told you that there's geometric mean and harmonic mean, but roughly speaking, it's giving that, okay? But it's not gonna be exactly that, okay? But this is arithmetic mean, okay? Now, mode mean where's the peak? So the peak can be here, let's say, that's the mode. Okay, where's the median? Okay, where's the median? Well, in this example, let me draw again. Let's make it obvious. Okay. Okay, if I were to draw like a mean, okay, I can do this and it probably will balance, right? But that's because you got really rich people here. But if I want to say, okay, let's take 50% of the population. Let me draw another one. Sorry, let's make it a very extreme. Right? Okay. So this looks like, because it's far out, you can get this thing to balance. But if I'm going to ask you, hey, find me where the guy in the middle is, what do you need to do? You need to make sure that the area here is 50%, right? And then area here is 50%. Okay. In this case, you will find out that median is much lower than the mean. Okay, so mean, median. Now, the reason that median and mean is not the same is because it has this kind of like rightward. This thing is called positively skewed. Okay, positively skewed. Okay, finally, you can think of two distributions. One's kind of like this, and one is kind of like this. Okay, and let's say I calibrate so that the mean is the same, standard deviation is the same, but this guy here is far out. This guy is far out. Okay, and that's called heavily kurtosis. Okay, now I'm gonna draw one perfect distribution. This distribution looks like this. You see this a lot, and I'll tell you why you see this a lot. But assuming I draw perfectly, okay? This, okay, this is what you would see if your histogram follow this and you fit this with the line. Oops. Okay, just draw this picture in your mind, okay? This picture, because this is the mean, I will call it mu. This sense here is called sigma, standard deviation. Now, my question is, because this is symmetric, what is the skewness? 0. Now, this thing will also have tail end dependence. By definition, kurtosis is equal to 3. Okay? What it means is that I calculate something like to the power 4, okay? And I normalize it, and I get exactly 3, okay? Exactly 3. Now, what it means is that this is my standard shape. And this happened to be, and you know, you don't have to believe me, but just take it as a mathematical trivial. This is a fact of life. Everything looks like this as a standard form. If you get something that is sort of like something like that, then you say it can have the same mean, maybe same standard deviation, also 0 skewness, but the kurtosis will be different. It would have excess or less than. So the term for it is excess kurtosis. It's kurtosis of that minus 3. Okay. So this is how you would normally think of the data. Okay. Okay. So these are the moments. Okay. So the moment, by the way, it looks like this. If I talk about the data, so the moment is x1 plus ... xn divided by n, right? Something like that, right? Whereas if you talk about central moment, it's xi minus x bar. This is x bar. And then to the power 1 or 2 or 3 or 4. And that's what I mean by central moment. Okay? Okay. Now, the data comes to you. The data comes to you. Okay? You don't get the control that it's going to look like that shape. Okay? So it can look like anything. Section 1.1.2, I think. 1.1.2, if you look in your notebook, is called scaling. Yeah, 1.2, scaling, okay? Scaling or normalization. I can't go back and forth that quickly, so you have to follow the book, okay? So 1.2.1, standardized by subtraction and division, okay? Subtraction and division. What it means is this, okay? Your data comes in, remember that axis, 1.107 to 82, whatever. It would make life easier if you kind of like standardize. So it's something like, okay, this is 0 and this is 1. Okay, how can you do that? Okay, in other words, the data can be anything like temperature, right? Temperature, you get some number like 25, 30, 40, okay? But I want to work it in a sort of like a standard way, okay? So I want to work with x in the value between 0 and 1. Obviously, I can force that, okay? So what do I do? Well, I can rescale everything, right? So I take the minimum, move it to 0, take the maximum, move it to 1. So that's one way of doing it, right? But most of the time in the data, you can use the moment to do that job for you. So if I have x, okay, and have mean of x, and I have standard deviation of x, why not kind of like centralize it, okay? So if, let's say my number is height, okay? The mean is 1.7, standard deviation is 30 centimeters, okay? So I had to work with something that looks like 1.6, but I want to work with something near 0. How would I do that? Well, I take everybody's height, right? Subtract from it 1.7 and divide by 0.3. So now I use this thing called, so now instead of X, let's call it U I equal to Xi minus X bar divided by S. Can I do that? And if I did that, it's going to be some people taller than average, shorter than average, right? So that's one way. Cool. So it's a common way of doing this. Now, why would you want to do this? You kind of ruin the dimensionalities. Why would I want to do this? In fact, why would I introduce it as 1.2? Because in the future, not that far in the future, you want to look at a bunch of variables together. And if the bunch of variables have very vastly different units, one is like a temperature unit, one's like a weight unit, and you just basically want to have a central plot of everything, it's a good idea to sort of like transform it. Okay, so that's kind of like a nonsensical reasoning. Okay, all you want to do is just put everything in the same page. Oh, that's easy. Just subtract everything by the mean and divide by standard deviation, and roughly you will plot everything in the same page. But there's more reason to it, because when you use this as a variable to feed in machine learning algorithm, sometimes you need to do this. Otherwise, it would have different effect on the model. Okay, think of y is equal to beta 1 x1 plus beta 2 x2. If x1 is meters in unit, x2 is centimeters in unit, then automatically there's a mismatch between the size of unit, right? So somehow you want all the variable to be kind of like on the same scale, okay? And in this section, that's why I introduced early, there's section of, so let me do this. So you can do this. This is one way of scaling, right? And so let's go to the book. Sorry, it's not that smooth of a transition. Okay. Right. So let's go to this in the book. Share. Okay. So now, okay. This is X. Can you see this? This is X. X is original number. Okay, original number. It's the histogram is like this. Okay. So what I do is I want to move it to the center, right? So how do I move it to the center? I subtract the mean from it. Okay. However, in this case, okay, this is subtract the mean from it. So it would be central. I can also subtract the median. Okay, nobody's stopping me. Nobody's stopping me, right? Because I kind of want to move it to around 0. Okay, and around 0 can be harmonic mean, geometric mean, arithmetic mean, median, right? So the whole point of this graph is to say you have a choice. Okay, for application like population statistics, maybe you want to centralize with the median. Okay, I just want to make that point. But most of the time you centralize with the mean. Okay. Likewise, when you want to sort of like squeeze the spread to be a normal spread size, you just divide by standard deviation. So a data set that has standard deviation of 2, when you divide by 2, it's going to sort of like squeeze it to the middle. When the standard deviation is less than 1, right? You divide by that, it's sort of like pushing it out a little bit. So that's why it kind of like scaling. Okay. So you can think of this thing here, the top thing here, as the location. And you can think of this thing as the scaling factor. So in other words, the factor you use on top relocate the center. And the factor on the bottom kind of scale the deviation, right? So this kind of like squeeze, this is a little bit too widespread, so squeeze it, okay? This one's squeezed by standard deviation. This one's squeezed by interquartile. Nobody's stopping you, right? So that's that's why I went through the whole length just to do this, okay? To say that you have option, okay? But for the rest of the class or for most of your career, you subtract mean and divide by standard deviation, okay? Now, you can also divide by what's called vector norm, and this is something that's a little bit more detailed. And this thing called distributional scaling, this is a little bit even more obscure. So I'm going to skip that for now. Okay, divide by vector norm, and basically distributional scaling is like you have this distribution. Let's do this. Let's make it uniform. So you kind of like do things by order. So you sort of like, not only do you squeeze, you kind of adjust so that you end up with a histogram that looks like a flat distribution. Okay, that's called distribution uniformize. Okay, just make it uniform. Anyway, so, and you can also, this is a little bit more than you need. Okay, let me just do a hand waving definition. Okay, so that's the data. Okay, that's the data. If you subtract the mean, okay, if you subtract the mean and divide by standard deviation, this is going to be centered around 0 and sort of like around ±1, but the shape will be the same. When you go to this way, you kind of like reorder, you make the data, you kind of like shift. The data is largest, you move to 1. The data is shortest, you move to 0. And then you just move everybody equal space. Does that make sense? That's called uniformize. So basically it's the ranking. Okay, so think about it. The bottom guy gets number 0. The tallest guy gets number 100. And the one in the middle gets number 0.5. So that's nothing but a rank. Uniformize basically is just ordering things by rank. However, there are reasons why. Sometimes you work with normal distribution. So this distribution doesn't look nice. You can also convert this so that bunch of numbers get in the middle and a little bit spread out so that in the end, it has that bell curve. Okay. Most of the time, you never do this. I'm just saying it's doable. And I want to put it as a numerical or program recipe so that you know how to use it. Okay. What it means basically is that you don't have to rely on the original number as long as you respect the relative rank. So in other words, if you are taller in the first scale, once you rescale, you're still taller, right? So something that's bigger here will be translated to something that's bigger here, will be translated to something bigger here. But the distance will move. So original is like the exact height. The other one is like a rank. The other one, the one to the right is like a rank, except you squeeze people in the middle together, right? So that you get this kind of bell curve. You can do that. You can do that. Not this is something that's not all that relevant in most applications. As a rule of thumb, when you have multiple variables, the first thing you would like to do is normalize it so that everybody is kind of like roughly on the same scale. And that normalization, usually 99% of the time, subtract the mean, divide by standard deviation. End of story. Okay? So I'm giving you the option, but in practice, to be honest with you, you just remember that you can subtract the mean, divide by standard deviation. Okay, and that's called standardized. Okay, standardized. Okay, fine. So that's all the sort of like raw number you want to play with. Now, let's go to topic of today. Now we have to, okay. Now from today we're going to cover the other two, which is probability theory and inferential statistics. Okay. Now, with Mathematica, okay, let's yeah, I'm sorry. Okay. I keep wanting to go to the blackboard. That's okay, don't worry. Okay, let's do this. Let's do this. When you have descriptive statistic, you have the numbers. You have the numbers. Essentially, you want to describe the histogram. Think of it that way, okay? Descriptive statistic is like drawing a histogram, but you can't draw it with pen or pencil, so you can draw it with taking the mean, draw it with taking a standard deviation, compute the skewness, compute the kurtosis, and imagine that. So you draw that in your head, right? So basically, descriptive statistic does that for you. It's a summarizing number. It's a set of number that summarizes a large set of number. You have 100 number summarized with the mean, second number, standard deviation, third number, skewness, fourth number, kurtosis. Based on that, you have a rough picture in your mind of what the histogram would look like. Okay, so that's from real number. Okay, that's from real number. Now the opposite side, this number in a way is random, right? Because you don't know what height the person is going to be. Okay, but the randomness comes from the data sample. Imagine now you in the driving seat of generating the data. So imagine that you have the power of God now. You toss a coin, and if it comes up head, you say, okay, next one is going to be a boy. You toss a coin, you come up tail, say, okay, next one's going to be a girl or something like that, right? Or you toss a dice, 1, 2, 3, 4, 5, 6, okay? If it come out 6, you say this person will be 1.7 meter tall. If it comes up 5, this person will be 1.6, okay? So imagine that now you're not getting the number from reality. Now you're generating the number, okay? Now you're generating the number. So it's like playing games, literally playing games, probability. So mathematicians come up with this concept. First of all, they agree that they call this thing called random event. Things that are random. Okay, things that are random is like head and tail, right? But they agree to sort of, well, they agree to say that anything that can happen is called sample space. Okay, it's called sample space. I know it has nothing to do with sampling, but it's called sample space. Okay, it's like anything that can happen. Anything that can happen. The probability of anything that can happen is non-negative. Let's agree to that. Okay, it's just a way of quotation. So probability anything can happen is non-negative. Okay. Second, okay, negative. This probability of anything that can happen in the possibility is negative, is non-negative. Second point, this is called second axiom. Probability of everything, that means the whole possibility, is 1. Okay, so there's no 110% sure. It's only 100%. So that's the probability of the sample space itself is equal to 1. So this is how I write it. Finally, probability of disjoint event, meaning events that if one happen, the other can't happen, can just add. So if I have a dice of 6 sides, probability of 1 or 3 is the same thing as probability of 1 plus probability of 3. Because the dice cannot be 1 and 3 at the same time. What's the probability of even number? Well, that's the same thing as probability of 2 plus probability of 4 plus probability of 6. And let's say it's 1/6 each. So that's 1/6, 1/6, 1/6. So that's 1/2. Okay. That's it. That is it. That's the name of the game. Now, the second concept, which I think I talked to you already last time, right? And this is something that I'll ask again on the midterm. Why is random variable not random nor variable? Okay, right? Why is it not random? Because I make it a rule that if I see a head, I call 1. Okay, I can't toss a coin, see head and call 1, toss a coin, see head and call 0. I can't do that. So it's not random. And it's also not a variable because it's actually a function. It's a function of reality to a number. Reality is a coin landing up with head. Function is 1. Reality is coin landing tail. Function is 0. Okay, so the function of that reality is 0, gives the value of 0. Okay, it's a function. And that function is not tricky, right? Every time you see a head, it's a 1. Every time you see a tail, it's 0. You can't switch. What is random is not random variable. What's random is nature itself. Okay? Why do we have this random variable? It's because, well, this morning I just talked about how AI is good in life because you can do all kinds of numerical analysis, but with AI, you can do analysis on word. Same thing here, right? I want to analyze probability of head and tail. The only thing I can do it using mathematics is to map event in reality to mathematics. So the random variable is created to map reality, which is what's random. Reality is random. Map the result of the reality to number line. Okay? In this case, if it's a coin toss, I might as well map it to 0 and 1. If it's a dice, I map it to 1, 2, 3, 4, 5, 6. Okay? The point is, now I have number line. And the value is what's random. Okay? Why do I do this? Because I want to model the probability with mathematical function. And mathematical function, you can't say f of head, f of tail, right? You can't do that, right? But you can do f of 1, f of 2, f of 3, f of 4, right? So that's it. Random variable is an interface, if you will, okay, from reality to number. The same way in AI, you have this thing called word embedding. It's a map from word or token in English language into number so that AI can compute it. Okay, so it's kind of like an interface. Okay, but once you have that interface, now the fun thing begins. Now it becomes like, hey, wait a minute. The rule of the game is probability of anything that can happen is non-negative. Probability of everything altogether is 1. Probability of 2 things that are disjoint can add. Instead of probability of head or tail, you say probability of 1, probability of 0. So now it becomes the rule is set. Okay, what's the 3 rule again? Non-negative, total 1, and disjoint can add. That's the rule. Mathematician, have fun. That's it, literally. We just say mathematician, have fun. And this is a good time to switch screen again. How do I do that? You have to do it quickly. Okay. So, okay. Let me say that again. Reality is what's random. I want to model reality. I want to create a function that gives it a sense of probability, but I can't give you probability of 1, probability of 0. So I have to map, sorry, I cannot give you probability of head, probability of tail, probability of stock market up, probability of rain. I can't do any of those. So I have to map event in reality into number. Once I map everything into number, right? Now, what's non-negativity? It means I don't go below this line. What is totality adds to 1? That means anything that happens here sum to 1, right? So with that rule in mind, let's say a mathematician comes up with this. -1, -11, 0, 7, and 8. Right, 80. Okay? And I create this function. And this function, okay? This function looks like this. Okay, this is 0.3, 0.4, 0.3, 0.2, and 0.1. Okay, I just made this up. I made this up. Question. Is this a valid representation of probability? Yes. Nothing is below zero. Nothing below zero. What's the probability of anything at all? 0.1 plus 0.4 plus 0.3 plus 0.2. What do I get? 1. Okay. And what's the probability of 7 or 80? Well, it's probability of 7 plus probability of 80, because 7 and 80 cannot happen at once. Has to be either, okay? And what's the total of that? 0.5. And any pair, any disjoint, this and this, you can add any probability, right? So probability, additive probability. Okay? So that's it. I invented a probability distribution function. I name it after myself. Okay, I named it after myself. The question is, once I die, who's going to care? Nobody. Because yes, it fits all the axiom, but it's not useful. Okay, so now the name of the game is, let's invent probability distribution function that satisfy the rule of the game, the 3-point, but is somehow useful. Don't ask me how, what does it mean to be useful, okay? Just say it's useful so that when you die, people remember your name. Okay, that's the name of the game. Okay, now I will then separate, go back to the first lecture. You have what kind of scale? What are the 4-number scale? It's going to be on a midterm, guys. What are the 4-number scale? Before that, nominal, ordinal, interval, and ratio, right? The first 2 is kind of discrete, right? The first 2 are discrete, right? And the second 2 are continuous, right? So I'm going to separate my world into here, discrete, and continuous. Okay, so the random variable can take on discrete or continuous value. That's what it means. Okay, so I separate into 2 worlds. Now the discrete, okay, discrete. Well, now I'm not going to separate between nominal and ordinal, because that's the meaning of it, right? That's how you define it. But I'm going to separate into 2 things. One is called finite, and infinite. Okay, finite, infinite. So finite means the value that it can take on say xk is finite. An example would be 0 for head, 0 for tail, 1 for head. Is it finite? Yes. Is it discrete? Yes. It's either 0 or 1, and it can't be anything else. It's finite. What about a dice? 1, 2, 3, 4, 5, 6. Is it discrete? Yes, it's discrete. Is it finite? Yes, it's finite. It's 1, 2, 3, 4, 5, 6, 7. 6, right? Now, what if it can be positive integer, like 1, 0, 1, 2, 3. Okay. For example, number of accidents in a year. Number of accidents in a year is a random event. Last year, there were 794 road accidents. The year before that, 1,214. The year before that, 55. Okay. What do you know about this number? Cannot be negative. Okay. Cannot be negative. So it can't go to negative. But can it go positive? Yes. How far can it go? You don't know. So it is infinite. But because it's countable, 1, 2, 3, 4, 5, I'm going to call it countably infinite. So think of something that has integer value. Okay. Now, technically, it doesn't have to be integer value, but it has to be discrete. So you can have some strange event that can be 1.2, 2.4, 3.6, 4.8. So it's not numerically an integer, but it is discrete, right? But think of integer, it's easier. Okay. So countably infinite. Okay. So this is what x can be, right? Okay. Continuous. Well, continuous means it can be, you know, anything, 1.1, 1.11111, 1.1112, right? Any number. I'm going to make 3 categories. It's infinite, but it's bounded. So for example, it's no smaller than 0. It's no bigger than 1. Okay. Now, why do I write that? Why don't I say something about no more than 100? Well, because you can stretch. Remember, that's the advantage of scaling, right? You can normalize, you scale. So let's do that. So this thing is called bounded. Bounded. Okay. What if it cannot be negative, but it can always be as big as you want? So that's called semi-bounded. And what if it's minus infinity to plus infinity? That's unbounded. Okay. What does this mean, basically? What does this mean? It means this. Might as well start again. What it means is that for discrete, your function looks like this. For continuous, your function looks like this. The difference is this is an absolute height, right? You add the height, sum the height equal to 1. That's the second rule. Whereas that rule, when you apply to continuous, it says integrate the area equal to 1. Okay, that's why you have to separate the rule, because mathematically it used 2 different devices. Okay, that's it. That's it. Now, obviously, if it's discrete, then this thing doesn't go on forever. Oh, sorry, if it's finite, it doesn't go on forever. This thing, likewise, it can be bounded from 0, 1, equal to infinity to minus infinity. Okay. Now you can try to be famous by creating mathematical function that satisfy those properties with respect to finite, countable, bound, semi-bound, and unbounded domain, right? You know what a domain is, right? The range, the value x can take on. That's it. You can invent this, and if it's legal, meaning, you know, non-negative, additive, and all that, and it's useful, you will be remembered forever after you die. The point is, there have been hundreds, maybe thousands of those. And I would tell you in this class, as a matter of tips, okay, like a hack, that you will only need to know about 10 of them. And that's good enough. That covers most of the situation. And today we'll start by running through them. Okay. Now, I want you to go to page. I'm not going to switch back because so let's go to, so this thing is called support of the probability distribution 2.1.3, right? There's finite discrete support and countable discrete support, right? And finite, countable, bounded, semi-bounded. Can you see that? That's section 2.1.3. So those are the 5 situations, 2 discrete, 3 continuous, right? So I'm going to ask you for that. Okay, so what are the 5 support? Which one are continuous? Really good, so forth. Okay, fine. Now, let's go to the catalog. This is like, I'm giving you a recipe. So go 2.2 probability distribution function. Okay. So now I'm going to start with probability mass function for discrete distribution. Okay. You may not have this info D. This is the header that I asked you, but what you have to do is, okay. In the notebook, info D is like my formatting. Okay, that's in page 1. So if you copy that, do it once. I think I sent it to you one time. But anyway, the point is, okay, the point is you go to declare this thing called binomial distribution. Okay, so what I'm going to do is do 3 things. Okay, 1, X. Okay, this is mathematics. This is mathematics. Okay, I am saying that X is binomial NP. What it means is that X is a random variable whose value can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to N. And that number is function, that function I'm going to create is useful because it describes a phenomenon in reality where you do a coin toss. Remember head and tail? Okay. So imagine now head and tail is a coin toss. 1 for head, 0 for tail, right? Now imagine that the coin is not symmetric. It doesn't have to be symmetric. It has probability P of landing head. So it could be 0.7. It could be 0.1. It could be 0.5. It has probability of a head. I toss that coin independently N times, and I count the number of heads. Okay? So let's say a mathematician invented this function. This function is very good for doing some kind of a casino bet or something, you know, with a coin toss. But why is it so useful? Why is it so useful? Because a lot of events are summation of binary events. How do you make a sales on a given day? You open your store, your customer comes in, he has a probability P of buying or not buying. Let's say that there are 100 people, each has a probability of buying equal to P. Okay, now you can make this adjustment customized so nobody has the same probability, but for modeling purpose, let's be simple. 100 people, you try to sell 100 people something. Each person has probability of buying P. Okay, how many can you sell? It could be 0. It could be 100, right? Or it could be some number in between. Well, let's say P is 0.1 and N is 100. It's going to look like this. 0, 1, 2, 100, and around 10, going to look like that. Okay, it's going to look like that. Why? Basically, you're adding a lot of head tail, head tail, head tail, head tail. Okay, so what's the probability of 10 sales? It's a probability of 10 sales and 90 no sale. Or it's also a probability of 90 no sale and the last 10 is sale, or any combination in between. Okay, every third one is a sale until you get to 10 or something like that, right? So add all that probability. So technically, so this is mathematics. Okay, this function, little p, now it's math, this p of x, and I did this before, I remember last class, and I want you to, again, I sympathize with you, but it looks very difficult. P of x is equal to n choose x. That's mathematical function. So that's what somebody invented as a mathematical function. Now, in Mathematica, this information is summarized by, well, look at your notebook, binomial distribution, right? So in Mathematica, you would write something like binomial distribution, open bracket, square bracket, n and p. Okay, n and p. Okay, that's it. Right now, by definition, is this a histogram? No, it's not. It's actually probability distribution, right? Right. So if you try to make a sales for 100 person every day, and you gather that data for the whole year and you plot, you know what's going to happen? Someday you make 5 sales. Someday you make 10 sales. It will be the case that if your assumption was correct, the histogram would look like this. It wouldn't be exactly like this. Okay, so let me say that again. The phenomenon is that you toss a coin, head, tail. Same thing as people come into your shop and buy or not buy with probability P and 1 minus P. Right? Same thing. You toss the coin, N equal to 100. Same thing as some guy walk into your store, 100 of them each day. Okay. Same thing, right? Same thing. Okay. Now, if I did this and I measure the data, right? I accumulate the data and I plot the histogram would look like my P of X. It wouldn't look exactly, it wouldn't match exactly, but it would look close to it. Okay. So this is going from probability to statistics. In real life, it goes the other way around. Let me say again. Okay. In this case, I specify 100 people. Each one has probability P. Okay. If this were the case, I'm God. I created this situation and I play it out for a whole year, 2 years, 3 years. And you go and open your shop. Every time you admit 100 people and buy, no buy, buy, no buy, and you just record the number of sales. Over a year, 2 year, do your histogram. It's going to look like that. Close to it. Close to it. See, that's because I told you. I'm God. I told you what N is. I know you what P is. P is 0.1. In real life, what happened? The other way around. You open your shop for a year, 2 years. And let's assume that every single day you have 100 customers. You come to the histogram. Then you ask yourself, what P would make my data most likely? See what I mean? It's the opposite, right? The first one, you start from function and you go to reality. But in reality, you start from reality, go back to mathematics. So the reality gives you the histogram. Then you ask yourself, which P, okay, you can choose P from 0.5, 0.6, 0.7, 0.8, 0.9, 0.10, 0.11. You can select any number and choose the P to fit the data. That's what we mean by probability model. Okay, probability model. Now, this is just one. So one situation is like this. Okay, now let me ask another. Let's say instead of opening your shop and admitting 100 customers and see how many sales you make, let's say you are manning accident report, like a car being, okay, the insurance company. And you write down every single day how many car accidents you got. How many car accidents you got. Okay? And then you do a histogram. Okay? You do a histogram. Chances are this function may work. Okay? But there's theoretical reason why another function is better. This function okay, this function, just watch my hand, x, instead of binomial, okay, and it's named after a guy named Poisson. Okay, again, because it's so useful, his name lives forever. Okay, that function looks like this. Okay, okay, it just happened to be this function. Now, why did mathematicians come up with that? Okay, very clever. Okay, okay, and this function will look a little bit like this. It's a little bit asymmetrical. It's very asymmetrical. Okay, that thing that we saw before, binomial, that's symmetric. This one is not asymmetric. Well, if you think about it, it makes sense, right? Because if you're talking about accident, you don't expect like a whole bunch of accident, right? So most of the time it's low number. So maybe on average, right? It's like 10 car crashes a day in city of Bangkok. Okay, most of the time it's less, 9, 8, 12. It's very rare that it's going to be like 50 accidents in one day, right? So it's going to have that kind of distribution. So this is what this one looks like. So this one also is nice because it is the other one, the value can be 0, 1, 2, up to n, right? So it's finite. This one is not. Because even though it's not likely you're going to have 1,000 accidents, there's no limit. There's no upper limit. So this is called countably infinite. Because you can have 0 accident, 1 accident, 2 accidents. You can have 1,000,000 accidents in a day. There's no theoretical limit. Okay, but probability-wise, no, you never see more than 10, let's say. Okay. So this is one. Okay. Now I'm going to run through this. Then when we go to, because I can't go back and forth that quickly. When we go to the notebook, I will run through them again, right? But this is the order, and I pretty much remember. So we already got an example of a finite, okay, binomial. There are other, but if you know finite, you're good, okay? countably infinite, okay, there are many, but if you know Poisson, you're good. Okay. What else? What about when you generate random number in Excel? That gives you what's called uniform distribution between 0 and 1, right? Well, I tell you what, let's call this distribution X beta with parameter alpha and beta. Don't worry about, in details. The whole point is that X belongs to, so this is big X is random variable, little x is the value, random variate, right? I'm going to ask that on exam. What's the difference between random variable and random variate? What's the difference between big X and little x? So this is what? Between 0 and 1. Okay. Now, why don't I just call random number like in Excel? Because this one is more powerful. This is called beta. This beta distribution, because you know the support, right? Okay. Again, this is going to be on easy question on exam. What's the support for this distribution? Bounded, right? Can be smaller than 0, can be bigger than 1. Okay. So all you need to do is draw this line, 0 and 1, right? It's going to be somewhere between here and here. And the value between it will have an area of 1. Okay. Well, beta is one of those. So if, okay. Every day, I don't know, it's a bad example, but I can't think of another good example. Every day you open up a bottle of whiskey and you run a bar. Okay. And at the end of the day, you measure how much percentage is left. So that's going to be the number between 0 and 1, right? Okay. You can't have negative. You can't have more than you start with. So it's going to be between 0 and 1. Well, record that for a year and do a histogram. You are going to be using beta with the right alpha and beta. Alpha and beta will adjust the shape. So this thing is a beta. That is the beta you see in your Excel. This is also beta. So is this. So is this. So beta is very flexible. Flexible. As long as it starts no smaller than 0, no bigger than 1. So as far as bounded support is concerned, when you run into a situation where the randomness is some kind of proportion of something, 0 to 100%, right? Empty bottle to a full bottle, right? Anything you have that kind of thing, beta is your friend. So you got 3 already, okay? Binomial, Poisson, beta, one of each, right? So based on, so what happened when you open the bar for 100 days, you just record how much of a percentage in that bottle you have left. And every day you start with a fresh bottle. Every day you start with a fresh bottle, right? And so today I got 50% left. Today I got 0. Today I got 25%. Just keep recording that number. You do the histogram, you will choose the alpha beta that fit that. Okay. 3. So now, fourth one. X is gamma. Gamma also has 2 parameters. So I'm going to call it alpha and beta. And gamma looks like this. So basically, gamma has a support of 0 and okay, gamma. Now, this is where I can give you another one, which is also useful. The other one that has similar kind of look is called exponential. Another one is called log normal. Okay, I'm just going to give you gamma for now. When I go to the notebook, your textbook would see in detail. Okay. So that's gamma. Finally, this is the most popular of all time, right? Okay. By the way, gamma will probably have a positive skew, right? Okay. So this is called normal distribution, N for normal. There's another one as well. It's called student T. Student, like it's in student. And that one has one more parameter. It's a little bit like normal, but it's more heavy tail. So that's called kurtosis greater than 3. Okay. So now you have 5 names. Okay. These are what you will be tested on. Because after all, if you got 5, you can go through life. Okay. There are 300, 400 of them. But if you know 5, you'll be pretty good. Okay. There are certain situations where this, okay, and now I'll show you how to work this thing. So this is what we call by probability model. Probability model in this case just simply means you draw a mathematical function that fits a histogram. And you know by the way your data comes, for example, your data is always proportion between 0 and 1, right? You know you're not going to go for normal distribution. No way, no way, right? You're going to go for the bounded distribution. And of the bounded distribution, there are many of them, but I only gave you one. So it's a little, so I'm not being too honest here. In theory, you should choose, right? You know your data is discrete, finite, discrete, countable, bounded, semi-bounded, or unbounded. That you have to know. Once you know, you have to select the probability from those sets. The thing is, even though there are many to choose from, you can only choose one because I only give you one example of each. Okay? Now let's see how it looks like in real life. Okay, so once again, discrete, continuous, finite, countable, bounded, semi-bounded, unbounded. Okay, binomial, Poisson. Now there's reason why the parameters sometimes use n, use p, use lambda. Don't worry about it. Okay. Beta, gamma, normal. That's it. Okay. In theory, there are many more. And altogether, about 300 of them, let's say. Okay. Okay. Stop share. So now let's go to your textbook. There it is. Okay. There it is. Okay. Basically, this info-D function is from the very beginning. This is the header file. I think I sent it to you a few months back. Sorry, a few weeks back. Basically, what it does gives you the mean, the variance, skewness, and kurtosis. Basically, just summary, right? Okay, except I add some kind of like a table around it. Okay, so there it is. Okay, the mean is NP. The variance is this, so standard deviation square root of that. Skewness is it. So this is actually something that can be computed, right? How do you compute this? Well, instead of adding, right? It's kind of adding the weighted, probability weighted value. Okay, but you can do that. So that's in your book. Okay, so now this is what it looks like. Normal distribution, right? So see, if n is equal to 10 and p is equal to 0.3, what's the mean? 3. So this comes from the formula, right? This is like this is a fact. So I can move this around. See? Right. Okay, so that's normal distribution. Okay. Then I skip to all the way to normal distribution. Okay. Again, I can move the means around. That means nothing. I can move this. Okay. Right. Okay. So I didn't give you all. I just gave you these two here because I'll go to detail later. But here's the thing. In Mathematica, and this is why you have your exam using this. And I want you to type this along with me. Okay. If I have this probability, okay, if I have probability, I can calculate exactly the probability that the value fall between here and there. How? Well, the probability of this is what? Okay, what's the probability that this random variable will be between 3 and 4? That's this height plus that height, right? Okay, so 0.26 plus 0.23, let's say. Okay, so you just add that. Okay. However, for continuous distribution function, do you add the height? No, you take the area under the curve. Well, the area under the curve can be very tricky because it involves integration function, right? So how do I work with this in real life? How do I work with this in real life? Well, there's mathematical formula, or because you use it all the time, Mathematica built this in. So for example, okay, let's do this. Okay, this character, now I want you to memorize this because this you have to enter this in exam, and I'm not going to ask, okay? If you do back, okay. Okay, let's say I'm going to name my distribution equal to, what do you want, guys? Let's make it normal distribution, let's say, okay? Normal distribution, open bracket, let's say 1.7, oops, 1.7, oops, where's my point? 1.7, comma, 0.2, okay? Close bracket, okay? Just type something like this, okay? What happened? Shift enter, nothing, okay? Except this thing now becomes black because now you know what it is, okay? So now imagine in your head, you see this, right? Normal distribution. So you think of the bell curve. This is the mean. The mean is 1.7 centimeter. So this is a height distribution, okay? And standard deviation is 20 centimeters, okay? By the way, as a rule of thumb, get used to saying this. If this is normal distribution, then 68% of the population is between 1.7 minus 0.2 and 1.7 plus 0.2. Okay, so when you see mean and standard deviation, that range established by mean plus minus one standard deviation should cover about 68% of the population. Okay, that's how you imagine things in your head. So 1.7, 1.5, 1.9, yeah, about 68% of the people in there. Okay, now you can ask it anything. I want to know probability that X, okay, X less than equal to 1.7. Let's make it easy. 1.7, comma, given that X. Now, in Mathematica here, big X and little x, you use the same X here, just for, for computer coding, there's no point making big or small in this case. Okay, backslash, open bracket, and type the word distributed. See that? It's going to give you auto suggest, so you can just tap. Okay, distributed. That's going to give you this quickly sign. You can enter this quickly sign from special character, but I want you to memorize this because it's used all the time. Okay. X backslash open bracket this, and it's going to give you autocorrect. This is saying that it's normal, my distribution. Okay. See that? So this is a declaration of n open bracket 1.7 comma 2 close bracket. To find probability of something x less than equal to 1.7, what are you doing? You are integrating from minus infinity to 1.7 the probability distribution function that has this. Okay, so that's what it means. Okay, and of course, because it's symmetric, half people will be 1.7 or shorter. By the way, you can less than equal or you can just less than, it means nothing because with continuous number, probability exactly at the point is the same, 0. Okay, so you can do that, less than equal. Okay, what if you want to sell a t-shirt for someone that's between 1.6 and, okay, you want to know how many people, okay, how many people or proportion? About 1/5. And you can do this anything, right? You can do anywhere, okay? You can say, what is interquartile, oops, quantile, right? X. You can ask, basically what happened is once you have this, it's like you've drawn that. You can ask any question, okay? So you can ask quantile of that distribution. You can, so the quantile function. Oops. Function. Oh, I don't want speaker. Hold on. Why did I just turn on speaker? Okay. So now you can do this. Okay. Now let me show you. Let me show you what this means. Okay. PDF of. Let's see if they can do that. Okay. PDF of this and X. See, this, by the way, is that curve. Okay. See, that's PDF. Right? If you don't believe me, we can plot it. X between 0 and 2. See? Okay, how about 1, 3? Okay, that's the distribution of height, right? By the way, sometimes instead of defining PDF, you can do CDF. CDF is basically probably something less than equal to that. So that's going to be like this, right? So basically, PDF is the integrate cumulative distribution function, right? Look at me and raise your hand if you don't know the difference between cumulative and CDF and PDF. So probability around the point is a density, right? But probability at that point or less than is cumulative. So basically integrate from minus infinity to that. Okay, that's CDF, the short term for it. Now, for discrete distribution, it's called PMF, right? For binomial distribution, it's called PMF. However, for Mathematica, because PMF and PDF is the same concept, they use the word PDF, okay? Same thing, the cumulative mass function is not an integration, but it's a summation. So it's CMF in mathematics textbook. But because conceptually it's the same thing, the function you use in here is also CDF. So let me show you what, so for example, let's say my, this is my, well, let's say a binomial, my binomial equal to binomial distribution. Okay, let's see, what's it? 100% and 0.1. Okay, right? So now I want to plot PDF of my binomial and X. Now X is going to go from where to where? From 0 to 100, right? Plot PD. What's wrong here? What's wrong here? Hold on, let's try. Oh, okay. It's too small. Okay. Let me make a different case. Let's make it 10. It's easier to show. Oh, it's discrete. Okay. I forgot it's a discrete. Okay. So there it is, right? 0. So if this is you sell to 10 people and probability of each sale is 0.1, then on average you sell 1. Okay. Now if I make this larger, then obviously, right? Let's make it normal 0.9. Okay. Okay. It's a very profitable shop. Then when you plot this, sorry, it's not just plot, it's discrete plot. .9. Okay, so a lot of time you sell, you make a lot of sales, and so now there, see, you sell a lot more. Okay. Okay, so that's how the distribution works. Now, so when you go to here, see, this is where you adjust the mean. Okay, fine. Probability and quantile. Okay, you know this quantile, right? Function. So this is basically the example you should keep in mind, right? So If you see this in the book, by the way, it's an open book exam, so you can take this book. Okay. So, right. Inverse CDF. Okay, this is CDF. Blah 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 blah. Okay, let me go to different cases. Okay, let's take a 5-minute break. Let's say assume that up to here, you understand with me, first of all, descriptive statistic, numbers that summarizes data set. So one number to summarize 100 numbers, two number to summarize 100 numbers. Basically, think of it as communicating histogram before you have a fax machine. Okay? So these are called descriptive statistics. Now, it doesn't sound like archaic as you think, because when you go to advanced area, for example, in finance, in mathematics, in engineering, it's the descriptive statistics that they report to you. Okay, let me say that again. I often make a joke, right? That you have 100 numbers. You can't send a whole 100 numbers, so you have to summarize it with one number because you have just a telegram. So take the mean, and you allow another number, take the standard deviation. Okay, that's kind of like simplistic view of what summary statistic is. But in finance, in engineering, in all kind of professional endeavor, accounting, whatever, you will be so used to specialized professional statistics that you will not be communicating with histogram. You will not be communicating with fax machine or picture of a distribution. You will actually just tell you, okay, right now my machine has performance statistic of 1.7, and everybody knows what that means. Okay, so descriptive statistic, I make a joke that it's just a summary. In real life, that's what professional people talk to each other on. Okay, it's like, a cop can say, oh, I stopped somebody and the alcohol level was 0.08. Knows right away what that means. That's blood alcohol. That's bad. That's good. That's illegal. That's toxic, right? So summarizing statistic, or what I call descriptive statistic, doesn't look like a big deal now, but in professional area, it is a big deal. Okay, but this depends. I can't teach you everything because, I'm not into crime statistics. I'm not into population statistics. I'm not into health statistics, but these are all numbers. During the COVID number, you would have heard of this thing called infectivity, R number. I don't know if you heard that. That's one of those things, right? Essentially, it's a summary before the histogram. So it's not trivial. Second thing, a probability model is like trying to figure out what the probability profile look like, but I want to do it with mathematics. So I have to turn reality, which is random, into number first. That's random variable. Once I have random variable, there are 5 domains of random variable, 2 discrete, 3 continuous. Now, based on that, the model is the mathematical function. And there are hundreds each. But I only gave you one. Now, let's go to a break. But before we go to the break, I want to take you to this Wikipedia page. Okay? Then we go to a break. Wikipedia, let's say normal distribution. Hang tight, I'm almost done. Okay, now this here describes normal distribution, right? It shows you, basically this one is not interactive because it doesn't have that thing that we play with, right? But, okay. So there it is. And that function, that exponential 2 PDF, you remember that? PDF, where's that? There it is. Okay, see that exponential 2? You saw that earlier. Okay, anyway, the point is this. If you go down to the bottom of the page, where's the bottom of the page? Bottom of the page, bottom of the page. There will be, there it is. See that? Okay. So far, you are living in this world, univariate, okay? Probability distribution, discrete, finite, discrete, infinite, or countable, right? Where's the one that I gave you? Binomial. Okay. Where's the one that has discrete but infinite? Poisson. 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 There it is. Okay. Poisson. So this one, binomial, Poisson. Again, you can have many other. There are hundreds of them. There are actually more than this, by the way, not just this. Continuous, bounded, beta. Semi-bounded, I call it semi-bounded or semi-infinite, gamma. Unbounded, the whole line, normal. And that's this page. Okay. Now, so if I go, for example, let's go to Poisson again. See that? Poisson, and that's, see that my formula? Lambda to the k or lambda to the x, e to the minus lambda divided by x factorial. In this case, you use the word k, not x. See that? Remember I wrote this down, right? Okay, it has that mean variance. Its skewness is positive, right? Excess kurtosis, 1 over lambda, right? So all this, again, probability mass function in Mathematica, it's called PDF, just the same. Okay. So what is this good for? It's good for things that you don't expect. So it's not like coin toss. Coin toss, you have probability P. This you have like probability lambda or something, but it's rare. Okay. So this is Poisson distribution. Again, so at the bottom, even, okay, go to the page Poisson. The bottom, you have the same menu, basically. So every bottom of every distribution function, at the bottom, there'll be a menu of them. Again, see? Finite support, binomial, countable, Poisson. It's black because it's this page. Bounded, beta. Semi-bounded, gamma. Real number line, normal. Okay. Another word for normal is Gaussian because the mathematician who came up with this function is named Gauss. Okay. Okay. Last note is some of these names are confounded. What do I mean by that? Remember I told you about a coin toss, right? And if I say I toss the coin n times, okay, so not just once, but n times, and the probability doesn't have to be 50-50, it can be probability P, right? So a coin toss generalized is Poisson, okay? Sorry, binomial. But if I generalize only P, but not N, in other words, one coin toss, that one is called Bernoulli. Why does Bernoulli get a name memorized, immortalized, even though it's so simple? It's because this Bernoulli was one of the very first person who has the concept of probability to begin with. So this was 500 years ago, okay? So that's why this coin toss, one toss, head or tail. If you don't make head or tail 50-50, but generalize to P, that distribution is called Bernoulli. Okay, and that name is immortalized because this Bernoulli invented this 500 years ago.
Okay, and everything else you will look here. There's a lot of name of people: Baldrick, Nicole, Bates, Maxwell, Conway, Poisson. These are all name of people. But if you click on any of these names, chances are it'll be very complicated because as they make later invention, they only become memorable if they are useful. The only funny thing is here normal and Gaussian are the same thing. The name the person is Gauss. But it's so normal. It appears all the time that there is this thing called central limit theorem. I'll talk to you about it later. It so happens all the time. It becomes normal. So it gets honored with the word normal. Another one is funny. It's called student. We're student. You know why it's called student? Because the guy who invented it wanted to be anonymous. So he submit this invention and say, I'm just a student. So that's why this name is called students. Okay. And you don't know what the name person is. It could be a group of a student. Okay. So it's a bit like in Bitcoin where you don't know who invented it. Okay. So this is kind of that. So now, so you can see that binomial, if you set n is equal to 1, is the same thing as Bernoulli. A lot of time you see relationship like that. Let me give you just one example and we'll go to break. This gamma here has two parameters, alpha and beta, or k and theta. If you set this one equal to 1, it becomes the same thing as exponential. Oops, sorry. Okay, so even though you see a list of a lot of numbers, some of them are kind of specialized case of another. Okay, so binomial NP, if n is equal to 1, it is Bernoulli. Gamma AB, if a is an integer, it's called Erlang. If a is 1, it's called exponential. Okay, but you don't need to know that. Okay, good. Let's go to a break, come back. When we come back, we'll flip it. We'll say, now we play God. Now we know what the distribution is we're going to generate. And then we go to multivariate random variable. Then we go to probability statistical estimation, and then we're done. Okay? Okay, go to your break.